4.5 billion years ago, in the part of the galaxy where our solar system would eventually settle, a cloud of gas and dust began to pull inward. There was no sound. There was no light of any kind that a human eye would have recognized. There was only the slow, patient action of gravity, the most unhurried of all forces, drawing the cloud's edges toward its center by increments too small to see, across timescales too long to feel. The cloud was cold, it was vast, and somewhere inside its drifting, formless mass, a motion had already begun that would not resolve for millions of years. The cloud stretched across a volume of space that would take light several years to cross in any direction. At its densest, it was still so thin that a human hand passing through it would have felt nothing, no resistance, no temperature, nothing but the silence of near vacuum, and yet it was not empty. Every cubic centimeter held hundreds of hydrogen molecules, traces of helium, and scattered through it like a fine dry powder, grains of solid material, silicates, carbon compounds, tiny crystals of ice. They did not glow, they did not move with any visible speed. They drifted in the dark, so slowly that a year of watching would have shown no change at all. The inward pull began at the cloud's center. Some disturbance, perhaps a nearby star's death, its shock wave pressing gently against the cloud's edge, had tipped the balance between the outward pressure of the gas and the inward pull of the cloud's own weight. Once tipped, the balance did not restore itself. Gravity is patient, and it does not stop. The center grew denser. A denser center pulled harder. The cloud contracted around it in a slow gathering spiral that would, over the course of 1,000,000 years, draw most of the cloud's mass into a flattening disk. The flattening came from spin. The cloud had always been rotating, very slowly, the way all clouds of gas in the galaxy rotate, picking up a slight angular drift from the motions of nearby stars and the slow circulation of the galaxy itself. As the cloud shrank, that rotation quickened, the way water spinning in a draining basin spins faster as it narrows. The outer regions, unable to fall straight in against the force of their own sideways motion, settled instead into a wide, thin plane, a disk, rotating, heated at its center by the compressing mass of what was becoming a star, cooler and dimmer at its edges, where the temperature fell toward the bare cold of interstellar space. This disk was not flat the way a sheet of paper is flat. It had depth, a thickness of gas and dust that tapered toward the edges, thicker at its inner regions and finer at its rim. It spanned a distance that would take the fastest spacecraft humanity has ever built, many thousands of years to cross. And within it, so much was still undecided. The dust had not yet gathered into planets. The gas had not yet been pushed away by the heat of the young star burning at the center. Every particle of solid material in that disk was still moving, still colliding, still choosing, by nothing more than physics, by nothing more than proximity and relative velocity and the particular charge on a dust grain's surface, what it would eventually become. The inner regions of the disk glowed orange with heat. Within the first fraction of an astronomical unit from the proto-sun, temperatures climbed high enough to vaporize nearly anything solid. Metal oxides survived. Calcium and aluminum compounds survived. Silicates condensed from the vapor like frost forming on glass, but at temperatures that would have melted steel. These were the most refractory materials, the ones that could hold their solid form even in fierce heat, and they formed first, close to the sun, before almost anything else in the solar system had taken shape. Further out, the disk cooled. At a distance of roughly 2.5 astronomical units from the proto-sun, temperature fell low enough that water could freeze. This was not a sharp line visible in the dust. It was a gradient, a slow change in the character of the material drifting through that zone. Inside this boundary, water stayed vapor. Across it and beyond, water became ice, and the grains of solid material in the disk changed character entirely, growing richer in volatile compounds that could not exist closer in. The boundary had no name yet. No one was there to name it, but it divided the disk into two different worlds of chemistry, and what formed on either side of it would never be entirely alike. A dust grain in that disk was almost nothing by any measure a human hand could apply. Its longest dimension was a fraction of the width of a human hair. Its surface was irregular, jagged at the microscopic scale, covered in chemical bonds that reached outward like tiny open hands. When two such grains drifted close enough, slowed by the same gentle currents in the gas, nudged by the random vibration of their own molecules, the bonds between them could catch, not with any force that could be felt, not with any speed that could be seen, but enough to hold. Two grains became one small cluster. The cluster drifted on and met another, and the bonds caught again. This was not collision in any dramatic sense. The grains were moving relative to each other at speeds of centimeters per second, the pace of a slow crawl. When they touched, no impact shattered them. The electrostatic forces on their surfaces drew them together gently, and they clung. The structures that formed in this way were porous and irregular, loosely packed like the delicate frost that forms on a window in cold weather. They were not solid. They were more like a lattice of loosely joined particles, full of empty space between the grains, held together by the weakest and most patient of forces. In time, these clusters settled slowly toward the middle of the disk, the plane where its mass was concentrated, where the gas was densest, and the gravity of the disk itself drew solid material inward from above and below. A dust grain falling toward this midplane through the disk's gas moved slowly downward, carried by gravity, slowed by the resistance of the surrounding gas, drifting like a particle of ash settling through still air. The journey might take thousands of years. At the end of it, the grain arrived in a layer that was growing thicker and denser as more material fell in from above. In this midplane layer, something began to change. The concentration of solid particles grew past a threshold. Clumps formed, not from the slow touching of individual grains, but from a different process entirely, a kind of spontaneous organization that physicists call streaming instability. Particles in the gas disk do not all move at the same speed. The gas moves slightly slower than the particles, which creates a headwind that gradually slows the particles' orbital speed and makes them drift slowly inward. Where particles happen to concentrate slightly, their collective gravity slows the gas more, and that slowing in turn draws more particles in. The concentration feeds itself. A dense knot of particles grows, pulling in more material from its surroundings, until the knot is dense enough that its own gravity can draw it into a cohesive body. This happened many times in many places across the disk, across millions of years. Each time a knot crossed the threshold, it collapsed rapidly by the standards of the disk, which meant over tens of thousands of years, rather than millions, into a body ranging from a kilometer across to tens of kilometers across. These were planetesimals, the first solid bodies in the solar system large enough to be held together by their own gravity, rather than by the fragile electrical bonds between individual grains. They were not spherical. They were lumpy and irregular, tumbling slowly through the disk, their surfaces raw and unprocessed, their interiors a compressed record of everything the disk had contained when they formed. The inner disk, closer to the sun than the frost line, produced planetesimals rich in silicate rock and metals. Further out, where ice had mixed with dust before the planetesimals formed, the bodies that coalesced were richer in volatile compounds, water ice, carbon dioxide, organic material that had drifted in from the cold outer cloud. Between these two populations, in the zone that would eventually become the asteroid belt, the material of the disk was transitional, not quite as refractory as the innermost zone, not quite as volatile rich as the outer disk. The bodies that formed there carried both characters in different proportions, depending on exactly where they had formed and how much material they had gathered. For a time, and the time involved was long by human measure, though brief by the measure of the solar system's whole history, the planetesimals in this zone grew larger by colliding and merging. A body 10 kilometers across swept up the smaller objects in its path and became 20 kilometers across and then larger still. The process was accumulative when the bodies involved were moving slowly relative to each other, when their orbits were nearly circular and their paths nearly parallel. In those conditions, a collision was gentle enough to add mass rather than subtract it. Gravity held the accreted material in place. The body grew. The proto-sun burned at the center of the disk, its light pressing outward through the gas and dust. It was not yet the stable, steady star it would become. It flickered and flared in the way that young stars do, burning unevenly as the gas surrounding it still fell inward and heated. Its light pushed outward against the disk's material, and over time that pressure, combined with the intense particle wind streaming off its surface, would begin to clear the gas from the disk entirely. But in this early period, the gas was still present, and its presence mattered. Gas drag slowed the relative motions of small bodies, keeping collisions gentle enough to accumulate rather than destroy. The region between roughly 2 and 4 astronomical units from the Sun was where the asteroid belt would eventually settle. In those first millions of years, it held far more material than it does now. The best estimates suggest that what eventually became the asteroid belt began with the equivalent of several times the mass of Earth in solid material, planetesimals, small bodies, pebbles, and dust spread across that wide annular zone. This material was not yet stable. It was still being sorted, still being stirred, still in the process of either building toward larger bodies or being disrupted by the gravitational forces that would shape what survived. The planetesimals that formed in the inner region of this zone were different in character from those that formed at its outer edge. Closer in, temperatures had been higher when the disk was forming, and the minerals that condensed from the gas were different. The calcium-aluminum-rich crystals that formed first, close to the proto-sun, were carried outward through the disk by its large-scale circulation, some of them reaching all the way to the outer asteroid belt and beyond, becoming inclusions within the bodies that formed there. The disk was not static. Material moved through it, mixed, was processed by heat and radiation, and settled finally into solid bodies that carried within themselves a record of the whole disk's chemistry. On the surface of a planetesimal, tumbling through the early disk, there was no atmosphere to diffuse the sunlight. The young sun struck the surface directly, intense, unfiltered, washing one side in heat and leaving the other in a cold so deep that gases from the disk could condense directly onto the surface as frost. When the body rotated, that frost evaporated. The heat built into the rock spread through it slowly and radiated back into space from the night side as long-wavelength infrared light. The planetesimal was warm on its day side and cold on its night side, and this imbalance, tiny as it was, already constituted a force acting on its orbit, a force too small to matter over centuries, but not too small to matter over millions of years. The disk itself was layered in ways that can still be read in the material that survives. Temperature decreased with distance from the center, but not smoothly. There were zones where the temperature gradient shifted, where different mineral phases became stable, where the chemistry of the condensing material changed character over a relatively short distance. The frost line was the most significant of these transitions, the boundary where water ice became stable in the solid phase, but there were others, less dramatic, associated with the condensation of different silicate minerals, different sulfide phases, different carbon compounds. Each zone left its mark on the bodies that formed within it. Through the gas of the early disk, a faint haze of very fine dust, the finest fraction of the original cloud material, remained suspended. Too small to settle quickly toward the midplane, this dust scattered the light of the proto-sun and gave the inner disk a faint, warm glow that would have been visible from far outside the solar system, the signature of a young planetary system in the process of becoming. Astronomers studying other young stars see disks like this around them, rings of scattered infrared light, marking the zones where dust is concentrated, gaps where larger bodies have begun to clear their orbital paths. The early solar system looked like this to any distant observer, a disk, a star, and within the disk, the quiet, unhurried work of accumulation. In the region that would become the asteroid belt, that accumulation was beginning to slow. The reasons were not yet fully in play. The great gravitational force that would eventually prevent a planet from forming there had not yet reached its full influence. But something in the dynamics of that zone was already different from the regions closer in, where the rocky planets were building rapidly. The relative velocities between bodies in the belt region were slightly higher, the collisions slightly more energetic, the rate of accumulation slightly less efficient. The largest bodies in the zone were growing, but not as fast as those in the inner regions. Something was resisting the process, gently from the beginning. In the outer disk beyond the frost line, a body was forming that would eventually weigh more than all the other planets of the solar system combined. It was accumulating rapidly. The ice in that region gave it abundant material, and its growing gravity drew in more and more solid matter from the surrounding disk. At the distance where it formed, the density of material in the disk was high enough, and the temperature low enough, that its core grew quickly, and as its core grew, its gravity extended further, reaching across the disk in long, invisible arcs. The belt region, hundreds of millions of kilometers closer to the sun, was already beginning to feel that reach, even before the body beyond the frost line had fully assembled itself. What the bodies in the belt zone did not yet know, and nothing knew anything, for there was no mind in any of this, only physics working at the pace of physics, was that the accumulation they were engaged in would never complete. The largest bodies in that zone would reach a certain size, and no further. The material that might have gone into building a planet would instead be stirred and scattered, and most of it would eventually be ejected from the solar system entirely, or swept up by the growing terrestrial planets closer to the sun, or sent raining down on the inner solar system in a long bombardment that would last hundreds of millions of years. What remained in the belt zone after all of this would be a fraction of what had been there, a small, cold, scattered population of bodies, none of them large enough to be round, except for one, each one a piece of a story that did not reach its intended resolution. The story it did not reach was planethood. That is the word that comes to mind when the process is described. Formation, accumulation, eventual differentiation into a core and mantle, and crust, the emergence of a full planetary body. In the inner solar system, that story reached its resolution. Venus and Earth and Mars grew from their planetesimals to become full planets, their interiors heated by the energy of accretion and by radioactive decay, their rock melted and sorted and resolved into layers. In the region of the belt, the story was interrupted at an early chapter. What survives there is not the wreckage of a planet that once existed and was then destroyed. That is a common misunderstanding, and the science does not support it. The total mass of material now present in the asteroid belt is tiny, roughly 4% of the Moon's mass, spread across a volume of space large enough to contain an orbit. There never was a planet there that was then broken apart. There was only the beginning of a process that was never allowed to finish. What remains is the threshold. That word carries something true. A threshold is not a failure, not a ruin. It is the place where two conditions meet, where one thing ends and another has not yet begun. The asteroid belt exists at that meeting place, between what the disk was and what the planets became. The bodies within it are not remnants of something lost. They are originals. They are the disk's own material, preserved at the stage of its becoming, held in the condition it was in before the forces that resolved the rest of the solar system into planets had finished their work in that zone. Each body in the belt carries, in its mineral structure and its chemical composition, a record of the disk from which it formed. The fine-grained carbonaceous asteroids in the outer belt are among the most primitive solid objects in the solar system, their composition barely altered since the day the disk's material collapsed into them. The more processed, rocky asteroids of the inner belt record a slightly later chapter, a time when the disk was warm enough to melt and differentiate the bodies that formed close to the frost line. Both kinds preserve something the planets no longer hold. The planets have been reworked too many times, their original material overprinted by billions of years of geologic activity, their surfaces and interiors remade. The asteroids have not been remade. What they were, they mostly still are. The disk that formed them was itself not permanent. Across the first few million years of the solar system, the gas that had cushioned the planetesimals' collisions and moderated their relative velocities was slowly cleared away. The proto-sun grew hot enough, its particle winds strong enough, to push the gas outward and eventually drive most of it out of the inner solar system entirely. Without the gas, the dynamics of the disk changed. There was nothing left to damp the velocities of the small bodies. Their collisions, no longer cushioned, grew more energetic. Accumulation became harder. Destruction became easier. The window in which a planet could have assembled in the belt zone was already closing, and with the gas gone, it closed further. The disk did not disappear all at once. It faded, the gas thinning over millions of years, the dust settling and coagulating until what remained was the solid population, the planetesimals, the smaller pebbles and boulders that had not yet been swept up by larger bodies, and the fine dust produced by collisions between them. This population was denser and more crowded in the earliest period than it is now. It was stirred and shaped and ground down over billions of years until it reached something closer to its present state, still rich in variety, still carrying within each body the record of its formation, but much smaller in total mass than it had once been. And within all of this, one body had grown larger than the rest. At the outer edge of the belt zone, where the material of the disk was richest in water and carbon compounds, a body had accumulated enough mass to pull itself into a roughly spherical shape, the point at which gravity dominates over the irregular structure of a tumbling rock pile. This body would eventually be called Ceres. It grew large enough to begin differentiating internally, its interior warming from radioactive decay, its ice melting and separating from its rock, the denser material settling inward, and the lighter material rising. It became, in the early solar system, not quite a planet, but something more than a simple asteroid, a world in its own right, quiet, cold, and carrying within itself a chemistry that the other belt bodies did not entirely share. But even Ceres did not finish its becoming. The same forces that prevented a full planet from assembling in the belt zone stopped Ceres from growing further. It reached a size and held it. Its interior settled into a cold and largely frozen state. Its surface, struck repeatedly by other belt bodies across billions of years, became cratered and old, and there it has remained, neither a full planet nor a simple rock, but a body balanced at a particular point of development, holding within itself the record of what the outer belt's material could become when given enough mass and enough time. The belt, then, is not a graveyard. This word is sometimes used, and it carries the wrong feeling. Graveyards hold things that once lived and no longer do. The belt holds things that were in the process of becoming and were paused. The bodies within it are not dead. They are suspended, not by any force applied to them, but by the absence of the condition that would have allowed them to continue. Without enough mass, without the stability of orbits that a gas-free disk and an undisturbed gravitational environment would have provided, the belt's material could not reach the next stage. It stopped where it was, and where it stopped is close to the beginning. The dust grains that formed from the original cloud material, the submicron particles that first clung together in the disk's midplane, are present within the bodies of the belt, not unchanged in their individual form, but preserved in the mineralogy of the rock that formed from them. The heat and pressure events that melted some of that material into the tiny spherical beads found within primitive meteorites are recorded in the rock. The composition of the gas that surrounded the disk when the material condensed is recorded in the trace elements within certain mineral phases. The temperature of the disk at the location where a particular asteroid formed is recorded in the mineral assemblage of its surface and interior. The belt is a library of the disk, each body is a volume, and most of them have never been opened. A single asteroid tumbling through the belt on its long elliptical path carries in the few kilometers of its diameter more information about the first million years of the solar system than all the rock on Earth combined. Earth has been reworked. Its oldest surface rocks have been swallowed by subduction, melted, and remade many times over. What little survives from the truly early period, the first few 100 million years, is fragmentary and chemically overprinted. The belt preserves what Earth cannot. It preserves the condition of the solar system before the planets were finished, before the processes that make planets habitable had erased the record of the processes that made the planets at all. In the cold and silence of the belt, far from any human instrument, and far from any atmosphere that carries heat or sound, the bodies drift in their slow ellipses. Some of them are nearly as old as the solar system itself. Their surfaces struck and restruck across billions of years, but their interiors relatively unchanged since the first few million years of the disk. They hold within them the conditions of a time before Earth existed, before the sun had reached its stable configuration, before the planets had found their current orbits. The belt exists in the present, but the bodies within it are a record of a past that no other material in the inner solar system still holds in such complete form. The disk that formed them eventually dissipated. Its gas was gone, driven outward and away. Its finest dust was either swept up or blown out by the solar wind. What remained was the solid population, irregular, varied, ancient, settling into the pattern of orbits it still traces today. The early solar system grew quieter. The large bodies in the inner disk grew into planets, their surfaces cooling, their geologies beginning. The outer disk produced the giant planets, whose gravity would, over long time scales, continue to shape the belt's population. And the belt itself became what it is now, a preserved middle chapter, held open at the same page across billions of years. The disk's own stillness, settling finally into a shape it has not abandoned. The cloud that began all of this is gone. It collapsed into what it became, and what it became dispersed across the whole span of the solar system, sorted by physics and chemistry into the different kinds of bodies that now occupy it. But the division between what fully formed and what did not, that division still exists, and it is still visible, and the material that holds it open is still there in the belt, drifting in the old cold dark between Mars and Jupiter, turning slowly on its own axis, carrying within its rock and ice and carbon the record of a disk that dreamed of more planets than it could finish making, and kept, in that unfinished zone, the earliest and most patient evidence of everything it once contained. Far beyond the inner planets, where the light from the sun has already thinned to something cooler and more distant, a young planet was growing. It was not the largest thing in that region of the disk. It was not yet visible as more than a thickening in the cloud of orbiting material. But its core had already formed, and its gravity was already beginning to extend outward into the surrounding space. And what happened next would determine the fate of everything within hundreds of millions of kilometers of it. Jupiter did not grow slowly. In the cold region beyond what astronomers call the frost line, the boundary in the early disk where temperatures dropped low enough for water to freeze onto solid grains, there was more material available than anywhere closer to the sun. Ice and rock together made a richer harvest than rock alone. The core that would become Jupiter gathered mass at a rate the inner planets could not match, pulling gas from the surrounding nebula in great sweeping flows, swelling past 10 times the mass of Earth, then 20, then further still, until it became something that had changed the rules of the solar system simply by existing. It had not yet moved. It had not yet done anything except become massive, and that was enough. The belt of material lying between what would become Mars and Jupiter was at this point still trying to build a world. Planetesimals, bodies ranging from a few kilometers across to hundreds of kilometers, were moving through that region in orbits that were still relatively close to circular, still gentle enough that collisions between them could sometimes result in accumulation rather than destruction. The conditions were not as favorable as in the inner disk, where Mars and Earth were assembling more efficiently. The belt region was more spread out, its material less dense, the collisions less frequent. But given enough time, there was no fundamental reason a planet could not have grown there. The arithmetic of accumulation was slow, and it was proceeding. Then Jupiter finished forming. The gravitational reach of a planet scales with its mass. Jupiter's reach, from the moment it reached its full size, extended across an enormous volume of space. It did not need to be close to the asteroid belt to affect it. Gravity does not require contact. It does not require proximity of the kind that bodies on a surface experience. Across hundreds of millions of kilometers of empty space, Jupiter's pull was a presence, not dramatic, not sudden, but steady and patient, and absolutely relentless in the way that physical law is relentless, which is to say, it never stopped. The orbits of the planetesimals in what would become the belt began to change, not all at once, not visibly, not even measurably over a single orbit, but Jupiter's gravity, acting repeatedly on a body that passed through a particular region of space at regular intervals, could accumulate. Each pass added a small perturbation. Each perturbation tilted the orbit slightly, stretched it slightly, changed the angle at which the body met its neighbors. Over thousands of orbits, over millions of years, these small perturbations grew. What had been nearly circular paths became elliptical. What had been gentle, accumulative collisions became something else entirely. A planetesimal, moving in a nearly circular orbit, meets another planetesimal in a nearly circular orbit at a relative speed of perhaps a few tens of meters per second. At that speed, two rocky bodies the size of small mountains can collide and sometimes stick together. Some of their kinetic energy is lost to deformation and heat. What remains is not enough to separate them. They become one thing, larger than before. This is how planets grow. This is the process that, repeated across millions of years and billions of collisions, assembled Earth. A planetesimal moving in a stretched eccentric orbit, its path tilted out of the plane shared by most of the disk, meets another body at several kilometers per second. And at that speed, the collision does not add, it subtracts. The energy released in an instant is enough to shatter both bodies, to send fragments in every direction, to convert what had been a slow accumulation of mass into a cloud of dispersed debris. The process reverses. The planet that was building begins to unbuild itself. And this shift in the character of collisions, driven entirely by Jupiter's patient gravitational reach, is what ended the belt as a place where a world could form. The word for this is resonance, where a body in the belt orbits the Sun in a period that is a simple fraction of Jupiter's orbital period, once for every 3 of Jupiter's orbits, or once for every 2, or twice for every 5. Jupiter's gravity arrives at the same point in that body's orbit at regular, predictable intervals. The tugs accumulate in the same direction, over and over, rather than averaging out. The orbit stretches, the eccentricity climbs. Given enough time, the eccentricity climbs high enough that the body crosses the orbit of Mars or Earth, or comes close enough to another massive planet to be flung entirely out of the belt. These zones in the belt, the places where these resonance conditions hold, are nearly empty today. They have been nearly empty for billions of years. The material that once moved through them was scattered or destroyed so long ago that what remains is absence, and the absence itself has a shape. Daniel Kirkwood, an American astronomer working in the latter half of the 19th century, first noted these gaps in the belt's population while studying the distribution of asteroid orbits in the 1860s. His data was limited by the technology of the time. The asteroids he could observe were the brightest and largest, a small fraction of the total population, but the pattern was there even then, and it was clear enough that he named it, and the gaps have carried his name since. What Kirkwood identified was a structure carved by a force that had been operating continuously for more than 4 billion years. The grooves in the belt's population were not accidents, they were signatures. The full explanation for those signatures came much later, in the mathematics of chaos theory applied to orbital mechanics. An orbit near a resonance is not simply tilted or stretched, it is unstable in a specific nonlinear way. Small differences in initial conditions, differences too small to measure directly, can lead to very different long-term outcomes. One body placed slightly inside a resonance zone might remain there for hundreds of millions of years before its eccentricity climbs high enough to escape. Another body placed slightly differently might escape in tens of millions of years. The chaos is not random, it is deterministic, evolving from precise physical laws, but it is unpredictable in practice, in the way that the behavior of a very complicated machine is unpredictable even when every component follows simple rules. The belt is such a machine. Jupiter is the part of it that never rests. From within the early belt, Jupiter would have appeared as a point of light. It was too far away for its disk to be visible to unaided eyes, had there been any eyes to look. But it was bright, brighter than anything else in the sky except the sun itself, and perhaps rivaling the sun in moments of particular planetary geometry. Its light was cold and steady, neither flickering nor shifting in color. It hung in the same part of the sky over centuries, moving only with the patient pace of its 12-year orbital period. It looked, from that distance, like something passive, something merely present. Its work was invisible. The force it exerted had no color, no sound, no warmth or chill that could be felt at the surface of a drifting rock. It arrived as a mathematical fact, as the slow accumulation of a direction in the motion of things that had no way to resist it. The belt lost most of its mass. Estimates of the original material in the belt region vary, but the total mass now residing there is a small fraction of what was once present. The current belt contains less than a quarter of the mass of the Moon, gathered across a region of space vast enough to hold several planets comfortably. Most of what was there was scattered outward into the outer solar system, or inward toward the Sun and the rocky planets, or flung entirely from the solar system on hyperbolic trajectories into interstellar space. The belt that exists now is what remained after the scattering, a sample, a residue, the last fraction of a much larger original population. That scattering did not end when Jupiter finished forming. It continued, and it changed character at least once in a dramatic way, in an episode that the solar system's surfaces still record. The planets of the solar system did not form exactly where they orbit now. In the early period of the solar system's history, when the disk was still present, and the planets were still embedded in the gas and dust that remained after their formation, there were forces acting on them that shifted their orbits over time. And the interactions between a young planet and the gas disk it moved through could cause the planet to migrate, to drift slowly inward or outward, to change its orbital radius over millions of years. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, formed at one set of distances from the Sun, and then moved to the distances where they orbit today. This migration was not orderly. The best current picture of how it happened involves a period of orbital instability among the giant planets, triggered when the resonances between their orbits were disrupted as the gas disk dispersed. In this picture, Jupiter moved slightly inward from its original position. Saturn, Uranus, and Neptune moved outward. The change was not enormous in absolute terms, but in terms of the gravitational resonances it created and destroyed, it was transformative. Bodies that had been in stable orbits found themselves in unstable ones. Bodies that had been safely outside the resonance zones found those zones expanding to include them. The inner solar system was showered with displaced material from the outer belt and from the population of icy bodies beyond Neptune's orbit, over a period lasting hundreds of millions of years and ending roughly 3,900 million years ago. The Moon's surface remembers this. The basins that dominate the near side of the Moon, the dark plains that the unaided eye sees as shadow on the full Moon's face, are the filled floors of enormous impact basins, formed when bodies large enough to excavate craters hundreds of kilometers across struck one after another in what must have been, by any measure, a sustained and violent period of bombardment. The craters overlap. The newer ones obliterate the rims of the older ones. The whole ancient surface speaks of an era when the flux of incoming material was much higher than it is now, and when the objects arriving were much larger than those that reach the inner solar system today. This period is known as the Late Heavy Bombardment, though that name describes an epoch rather than a single event. It was not a bombardment in the way that word might suggest, not a sudden brief storm of impacts, but a prolonged elevation of the impact rate, stretching across hundreds of millions of years, gradually declining as the reservoir of displaced material was depleted. To stand on a surface during that era would have been to live in a world of slow geological violence, punctuated by impacts that came months apart or years apart, not minutes. The sky would not have been raining rocks in any constant way, but on the time scale of planets, the epoch was an event, a distinct chapter in the solar system's history, bookmarked at its beginning and its end by the specific orbital rearrangements that triggered it and the quiet that followed when the reservoir was spent. The belt survived all of this. It was diminished by it, scattered further, its population reduced again, but it was not emptied. The bodies that remained were those that had found orbits stable enough to persist across the disruptions, orbits that lay in the quieter regions between the resonance zones, orbits that were not too circular and not too eccentric, not too close to any particular gravitational threshold. What the belt contains now is, in a sense, the set of bodies that passed a long series of orbital stability tests over 4 billion years, each test conducted by the steady, unrelenting examination of Jupiter's gravity. The Kirkwood gaps, as they appear in any modern map of the belt's orbital distribution, are nearly empty lanes cut through the population at specific distances from the Sun. The exact distances correspond to the resonances at roughly 2 and 1/16 astronomical units, the 3-to-1 resonance at roughly 2.5 astronomical units, the 5-to-2 at roughly 2 and 8/10 astronomical units, the 7-to-3 at roughly 3 and 2/10 astronomical units, the 2-to-1. These are the places where Jupiter's gravitational timing is most powerful, where the accumulated perturbations run fastest and deepest, where orbits that began as stable have been systematically destabilized and cleared. They look in a diagram of the belt viewed from above the solar system like grooves worn into a wooden surface, smooth-edged, consistent, deep in the sense of being profoundly depleted, and the grooves run all the way back to the beginning of the solar system's history as a fully formed planetary system. What lives in the gaps today? Very little. A body placed in a Kirkwood gap resonance does not stay there for geological time, and its orbit grows more eccentric over millions to hundreds of millions of years, depending on the specific resonance and the body's particular initial conditions, until the eccentricity brings it into the vicinity of Mars, or crosses it into Earth-crossing space, or hands it to some further perturbation that sends it sunward. The gaps are not so much empty as they are constantly draining. Bodies that wander into them from adjacent, more stable orbits are slowly processed through the resonance, their orbits stretched until they exit not through the gap's inner or outer edge, but through the inner solar system, arriving as near Earth asteroids or occasionally as meteorites. The rock that fell on a field or on a desert or into the ocean, the rock that someone found heavy and dark and pitted with a crust of fusion where the atmosphere had burned it on the way down. That rock almost certainly came through a Kirkwood gap. Its last stable address in the main belt was somewhere adjacent to one of those lanes, and over millions of years the Yarkovsky effect, a gentle thermal push that comes from the uneven way a rotating body emits, infrared radiation, nudged it slowly toward the resonance. Once inside the resonance, the process was no longer gentle. Jupiter's accumulated perturbations took the orbit and stretched it, and the body that had rested in the belt for billions of years found itself in a mere few million more on a trajectory that intersected Earth's path around the Sun. The meteorite, when it fell, carried 4 billion years of history inside it. It carried the mineralogy of its parent body, the record of the temperatures and pressures and chemical conditions that existed when it first formed in the early disk. It carried the signature of its particular path through the belt, the evidence of the impacts it had survived, the record of any brief period when liquid water may have moved through it as its parent body warmed. All of that survived the fall. The fall, what brought it here, what set its final trajectory, was the resonance, and behind the resonance, Jupiter, still working, still patient, still doing what mass and gravity do across any distance given sufficient time. To think of the Kirkwood gaps as absences is accurate but incomplete. They are absences, yes, regions where the expected distribution of bodies thins to almost nothing, where the expected density of a uniformly populated belt simply drops away. But they are absences with a mechanism. They are the visible record of a force that has been applied continuously for more than 4 billion years to every body that passed through that region of space. The gaps are not empty because nothing formed there. They are empty because what formed there was systematically removed, not quickly, not violently by any single event, but steadily, methodically, the way water removes stone by running over it in the same channel for an age. In 1866, when Kirkwood first noted the pattern, this explanation was not available. The mathematics of resonant chaos had not been developed. The connections between the gaps and the population of near-Earth asteroids had not been established. The role of Jupiter in shaping the belt was understood in outline. The broad gravitational dominance of the outer giant was not a new idea, but the specific mechanism by which Jupiter's resonances had carved particular, precise lanes in the belt's orbital distribution was not fully articulated for another century. Kirkwood identified the structure. The explanation came later, in small pieces, assembled by many people over many decades, each piece requiring different tools and different mathematics. The gaps themselves were patient enough to wait. A body at the inner edge of the 2-to-1 resonance gap, orbiting at roughly 3 2/10 astronomical units, completes 2 full orbits around the Sun in the time Jupiter completes 1. Every time that body returns to the point in its orbit closest to Jupiter, Jupiter is in the same place. The gravitational tug at that point is always in the same direction relative to the body's orbit. Across hundreds of millions of years, across hundreds of millions of such encounters, the tug accumulates. The orbit's eccentricity climbs. The body's closest approach to the Sun grows tighter, and its farthest distance grows longer, and eventually the orbit becomes something entirely different from what it began as. Not a near circular path through the middle reaches of the belt, but a long looping ellipse that dips into the inner solar system and swings far outward again. And then something else perturbs it further, and the path changes again, and the body that formed in the cold quiet of the early disk finds itself years or millions of years later closing in on the warmth of the inner planets. This is where the meteorites come from. Not all of them, but most of them. The inner solar system is not far enough from the belt to be safe from it, and it never has been. Every rocky surface in the inner solar system carries the record of that ongoing exchange. The craters, the chemical signatures, the fragments of asteroid material mixed into the regolith of every airless moon and planet. Earth's surface is mostly geologically active enough to have erased the direct evidence, but the ocean floor and the ice sheets and the deserts where meteorites fall and are preserved in cold, dry conditions all carry pieces of the belt's ongoing export. The belt is not static. It is leaking, steadily, through the gates Jupiter built. The gaps in the orbital distribution of the belt are quiet now. A diagram drawn today looks much the same as a diagram drawn 1 million years ago, or 1 million years from now, because the process that maintains them is continuous and the timescales of significant change are long. The gaps do not slowly close. The material that would fill them is removed as fast as the resonances can work, which is steadily, persistently, over millions of years at a time. What enters the gap zones from adjacent stable populations is processed through and ejected into the inner solar system, or lost to Jupiter's direct gravitational scattering, or ground to dust by the collisions that a high eccentricity orbit eventually makes inevitable. The gaps persist because the process that created them has never stopped. Jupiter moves through its orbit today on the same path it has held for billions of years, its gravitational field extending out through the solar system in all directions without diminishing, without resting, without any awareness of the work it has been doing since it formed. It is not a sculptor, not an architect, not something that made choices about what the belt would become. It is simply massive, and mass curves space, and things that move through curved space follow the curves, and across time enough those curves can be the difference between a world that formed and a world that did not. The belt is what remained when the curves ran through it long enough to clear everything they could reach. The dark lanes in the belt's orbital map, those clean, persistent absences, are in the end a kind of writing, not a message, not an intention, but a record. They record the mass of Jupiter, the period of its orbit, the age of the solar system, the timescales over which gravitational perturbations accumulate. Every detail of their structure encodes something true about the system that produced them. To read them is not to find a purpose, but to find a history, and the history they carry is older than Earth and quieter than anything that can be seen directly, and it is written in the places where something is not and has not been for longer than there have been eyes to notice the absence. The Kirkwood gaps are not wounds, they are not losses, not scars, not the record of a catastrophe. They are the shape that time and mass and orbital mechanics make when they work together across 4 billion years without interruption. They are the belt's most legible feature. They are what the belt looks like when you understand what made it, and when you let that understanding settle slowly into the picture rather than rushing past it towards something more obviously dramatic. The drama is in the patience. The drama is in the spans of time over which forces that could not be felt, could not be measured, could not even be named until recently, moved mountains from one part of the solar system to another and left their record in the quiet geometry of what was no longer there. Those quiet lanes, those steady gaps persist in the belt tonight, as they did last night and as they will tomorrow, and for millions of years in either direction, cut into the orbital population of a remnant disk by a force that will not stop, maintained by the mass of a planet that formed in the cold beyond the frost line and changed the arithmetic of everything it could reach. The belt turns around the sun in its slow, wide orbit. The gaps hold their shape, and in the lanes between them, the remaining bodies drift on orbits that have survived everything that could not. On the first night of a new year, in a city built on a hill above the sea, a man sat in the cold and looked up. The observatory at Palermo stood above the rooftops and the harbor, and the sky above it was clear with the particular clarity of winter when the air draws tight and the stars hold still. The astronomer Giuseppe Piazzi had been working through a catalog, moving his instrument from point to point across the sky, recording positions. It was methodical work. It was the kind of work that asks nothing of the night except that it remains still and dark and cold. And then one point of light, among all the fixed and silent others, was not quite where it had been the night before. It was a small displacement. Most eyes, even careful ones, would not have noticed. Piazzi noticed. He watched the point again the following night, and again the night after that, and the displacement continued, slow and consistent, as if this particular star had decided to walk. Stars do not walk. The planets do. They wander against the fixed background of the sky, which is why ancient observers named them wanderers. But Piazzi's moving point was not in the position of any known planet, and it moved too slowly to be what he first suspected, which was a comet. It moved like something in between, something with no clear category yet assigned to it. He had found, on the first day of January in the year 1801, a world that no one had been looking for. Nearly 2 centuries of reclassification would follow. For a time, Ceres was called a planet. Then it was demoted to asteroid, as more bodies were found nearby, and it sat in that category, unremarkable in name if not in size, for the better part of 200 years. Then, in the summer of 2006, the International Astronomical Union assembled to sort out what a planet actually was, and in the course of that reckoning, Ceres was moved again, not back up to planet, but sideways, into a new category built for worlds like it. Dwarf planet, a body large enough that its own gravity had pulled it into a sphere, but not large enough to have cleared the neighborhood of its orbit of other bodies. The name feels modest, the object is not. Saproges sits at the center of the asteroid belt, the largest single body in that whole wide region between the orbits of Mars and Jupiter. Its average width is just under 600 miles. In the context of the solar system, that is a small thing, smaller than the continental United States, smaller than the moon. From the surface of Mars on a dark night, it would appear as a faint point of light, barely distinguishable from the field of stars behind it. Nothing about its appearance, even through a powerful telescope on Earth, suggested that it might be a world of unusual depth. It looked like a gray, battered sphere, scarred by impact craters, cold and inert. The cold is real, the inert is not. At a distance of roughly 2.5 times the distance from the Earth to the Sun, Ceres receives very little warmth. Its surface temperatures swing between roughly -140 and -30 degrees Celsius, depending on the season and the position of the sun, and its average is closer to the coldest end of that range. There is no atmosphere to hold warmth, no liquid water on the surface, nothing that looks at first inspection like the conditions under which anything familiar to chemistry could endure. And yet Ceres has been doing something, quietly and continuously, for billions of years. It has been holding water, not on its surface. Inside, the best current picture of Ceres's interior is built from 2 sources of evidence: the way its gravity tugged on spacecraft passing near it, which revealed how its mass is distributed from center to outer shell, and the way its surface deformed over geological time under the slow pressure of what lay beneath. Both lines of evidence point to the same conclusion. Beneath its rocky outer layer, Ceres holds a mantle that is rich in water, ice, possibly mixed with salts and clays, and the fraction of Ceres' total mass stored in that icy interior may be somewhere between 1/4 and 1/3. If those estimates are correct, and the evidence is strong, if not yet absolute, then Ceres holds more fresh water than exists on all of Earth. Not more water per unit volume, more water in total. A sphere less than 600 miles across, cold and alone in the outer belt, carrying within it the largest freshwater reservoir in the inner solar system, locked in ice and salt and time. The density of Ceres is what first suggested this. A rocky world of this size, made entirely of silicate minerals and metal, would be denser than Ceres is. When Piazzi found it, and when later observers measured its size more carefully, the numbers never quite added up the way pure rock would predict. Something lighter was included in the mix. Water ice is lighter than rock. The density of Ceres sits at roughly 2,160 kilograms per cubic meter, less than half the density of Earth, notably less even than the Moon. The numbers left room for a great deal of something soft and cold. That water did not arrive from outside, not in the way it sometimes arrives on rocky worlds, as a gift from passing comets. Ceres formed with it. When the protoplanetary disk was sorting itself out by temperature, the region where Ceres formed was cold enough that ice could survive in the grains and pebbles that gathered together to make the larger body. Ceres is, in this sense, a fossil of conditions at the frost line, the threshold in the early solar system where water stopped being vapor and became solid. It formed at the edge of the cold, and it brought the cold with it. What happened after formation, though, was not purely cold and still. In its early history, Ceres experienced internal heating. The source of that heat was not volcanic in the way that word usually implies. No tectonic plates, no upwelling magma. Instead, the heat came from the decay of short-lived radioactive isotopes that were present in the early solar system in significant amounts and have long since spent themselves entirely. As those isotopes decayed, they released energy, and that energy warmed the interior of Ceres from within. In a body made partly of ice, internal heat means something specific. It means the ice melted, not everywhere, and perhaps not for long, but for a time, perhaps hundreds of millions of years, perhaps intermittently and longer. Liquid water existed inside Ceres, pooling in its mantle, dissolving minerals from the surrounding rock, acquiring salts and carbonates, and other compounds that water picks up when it sits in contact with stone. The water that moved through Ceres's interior was not pure. It was brine, and brine, unlike pure water, remains liquid at lower temperatures, which means it could persist longer and move further before freezing again. That ancient movement of water through the interior of a small cold world, 4 billion kilometers from the warmth of the sun, left a record. The record is visible today from orbit, and finding it required sending a spacecraft to Ceres for the first time, crossing the belt over the course of 3 years, and placing an instrument capable of reading the surface chemistry from above into a stable orbit around a world that had never before been visited. The spacecraft was called Dawn. It arrived at Ceres in the early months of 2015, and within weeks of achieving orbit, it began sending back images that resolved a detail that had been visible as a smear of light in ground-based and space-based telescope images for decades, a bright spot, or what appeared from a distance to be a single bright spot, somewhere on the surface of Ceres. As Dawn's orbit tightened and the images sharpened, the spot became 2 spots, and then several, and then the full picture resolved into something stranger and more specific than anyone had quite anticipated. There is a crater on Ceres, approximately 92 kilometers wide, roughly the distance a car might travel in a little over an hour of highway driving. The crater is called a Korka. Its floor is dark gray, the color of old stone, heavily shadowed by its own walls. But at the center of that dark floor, and scattered across a portion of it, there are patches of material so bright they seem almost to glow. The central deposit especially, a dome-shaped mound of bright material rising slightly from the crater floor. reflects sunlight with an intensity that stands out against the surrounding gray surface, the way a struck match stands out in a dark room. Dawn's instruments analyzed the composition of those bright deposits, and what they found was sodium carbonate, salt, the kind of salt that forms when brine, water-carrying dissolved carbonates, migrates toward the surface and then evaporates into the vacuum, leaving behind a thin crystalline residue. The water is gone, taken by the vacuum of space the moment it reached the surface. But the salt it carried remains, deposited in layers over a period that Dawn's scientists estimate may span thousands of years and may still be ongoing. A Catter crater is not an old scar, sealed and frozen in the past. It is a place where something is still happening. The mechanics of how that brine reaches the surface begin deep below the crater floor. The impact that formed Occultator did not simply leave a hole. It fractured the crust beneath it, and those fractures created channels, pathways through the cold rock and ice that had not existed before. Somewhere below, in pockets where the internal conditions are warm enough, brine that has persisted from the early history of Ceres, or that accumulates slowly through partial melting of the ice-rich crust, finds those channels. It migrates upward, molecule by molecule, pulled not by intention but by pressure, differentials, and capillary forces within the fractured rock. The journey is slow. Some of it refreezes partway and waits. Some of it reaches the surface. At the surface, it meets the vacuum immediately. There is no atmospheric pressure on Ceres, nothing to keep a liquid stable. The water in the brine evaporates, not boils, exactly, but sublimes, passing directly from liquid to vapor, and then dispersing into space. What it leaves behind is the salt, settled onto the crater floor in a thin, bright layer, layer on layer, over thousands of years of slow upward migration. The deposit grows. The dome at the center of a crater is built of this patient mineral exhale. In 2014, a year before Dawn arrived, a different instrument saw Ceres in a different way. The Herschel Space Observatory, which was a European space telescope designed to observe the universe in infrared and far infrared wavelengths, turned its attention to Ceres and detected something rising from its surface. What Herschel measured was water vapor, not liquid, not ice, but water in gaseous form, escaping from the surface of Ceres at a rate of approximately 6 kilograms per second. 6 kilograms per second is not very much. It is less than what a garden hose delivers, distributed across the surface of a world nearly 600 miles across. But it was real and repeatable, and it made Ceres the first confirmed object in the main asteroid belt to outgas water into space. The belt had been considered broadly a dry place, a region of rock and metal and dust, its volatiles largely spent. Ceres quietly contradicted that assumption. The outgassing is not uniform. Herschel's measurements suggested it came from particular regions of the surface, possibly from areas where the ice-rich crust is closer to the surface and exposed to enough solar warmth to sublimate slowly. Ceres does rotate, once every 9 hours or so, and as it turns, different faces meet the weak but real warmth of the distant sun. In those moments of solar exposure, the surface heats fractionally. Fractional warming, on a body made partly of ice, is enough. Something else about Ceres' surface records its watery interior in a subtler way. On worlds that have been bombarded over billions of years, and every solid body in the solar system has been, the oldest, largest craters should be the most obvious features, their deep basins preserved by the cold and the absence of erosion. On the Moon, the oldest impacts left basins hundreds of miles across, still clearly visible after 4 billion years. On Ceres, The oldest large impacts have partially disappeared. The expected deep basins are shallower than they should be, or have softened at their edges into gentle depressions rather than sharp-walled craters. The explanation for this is called viscous relaxation. Ice, unlike rock, is not perfectly rigid over very long periods of time. Under pressure, and given enough time, ice flows. Not fast, nothing about this process is fast. But over hundreds of millions of years, a crust that contains significant ice will slowly creep under its own weight, particularly in the deep structures of large impact basins, where the pressure from the overlying material is greatest. The walls of an ancient crater made of ice-rich crust will slowly settle, the floor will slowly rise, the sharp geometry of the original impact will blur, soften, and eventually become a gentle bowl rather than a steep basin. Ceres has been doing this for a very long time, quietly reshaping its own face from within, the ice in its crust moving in the same slow way that glaciers on Earth move, except slower, colder, and in the dark. This is what makes Ceres different from the rubble of the belt around it. The other bodies, the hundreds of thousands of irregular rocks and boulders and mountain-sized fragments that share its orbit or nearby orbits, do not have enough mass to do this. They are too small, too rigid, too cold, even in their cores, to allow the kind of internal movement that Ceres has experienced. They hold their scars. They keep the precise record of every impact they have suffered. Ceres erases its oldest wounds, slowly, from beneath. The Dawn mission lasted nearly 4 years in orbit around Ceres, and it surveyed the surface at increasingly close range, mapping the topography, measuring the composition, counting the craters and the bright spots, and the geological features that no one had seen before. Among the instruments Dawn carried was a visible and infrared mapping spectrometer, which measures the way the surface reflects and absorbs light across a broad range of wavelengths, and from that reflection profile allows scientists to identify the minerals and compounds present in the top fraction of the surface material. Near a crater called Ernutet in the northern hemisphere of Ceres, Dawn's spectrometer detected organic compounds. The word organic in chemistry means specifically compounds that contain carbon-hydrogen bonds, the molecular framework that all known life uses as its structural backbone. Organic compounds are not themselves life. They are not evidence of life. They are chemistry, and carbon chemistry can occur through purely geological and astrochemical processes without any involvement of biology. But they are the molecular precursors of life, the raw material from which, under the right conditions, more complex chemistry can build. And finding them on Ceres placed Ceres among a small number of extraterrestrial bodies, where organic material of likely indigenous origin has been directly confirmed. The exact nature of the compounds near Ernutet crater has been debated since the detection. The spectral signature is consistent with hydrocarbon-bearing materials, possibly aliphatic organics, the kind of carbon chain molecules that appear in carbonaceous meteorites and in the ice-rich outer solar system. Where they came from is not entirely settled. One possibility is that they formed on Ceres itself, in the liquid water environment that existed in its interior during the period of early radioactive heating. Water plus minerals plus organic bearing materials in a warm environment for a long time is one of the recipes that laboratory experiments suggest can generate complex organic chemistry. Another possibility is that they arrived from outside, delivered by impactors from the outer solar system where organic-rich material is more common. A third possibility is that both contributed. The compounds are there. Their exact origin remains an open question, spoken calmly, without urgency. What is not uncertain is the concentration. The deposits near Ernutet are among the most organically rich surface patches detected on any small body in the inner solar system. They are concentrated, not uniformly distributed across the surface, but gathered in particular places, in a pattern that some researchers have linked to subsurface processes, bringing material upward rather than surface delivery from above. The same deep internal movement that carried brine to the surface at a crater may have carried other materials as well over long time. It is worth staying with this image for a moment. A world less than 600 miles across, alone in the cold belt, orbiting the distant sun in just over 4.5 Earth years, has been quietly conducting chemistry in its interior for billions of years. The water it formed with melted, moved through the rock dissolved minerals, carried carbonates to the surface, and then froze again as the internal heat faded. The organics it collected or produced in that warm, wet interior period have been preserved in the cold ever since, held in a crust that is too cold for anything to happen to them now, too cold for them to react further, too cold for them to disperse. They are waiting, in the way that things with no awareness wait, simply by being present and unchanged. The cold of the belt is not incidental to this preservation. It is the mechanism of it. At the temperatures Ceres experiences, averaging somewhere around minus 100 degrees Celsius across most of its surface, chemical reactions slow to rates that are effectively zero on any human timescale. The organics detected by Dawn's instrument near Ernutet are in a state of extraordinary chemical stability. They have been sitting in that same molecular configuration, without reacting, without degrading, for perhaps 4 billion years. The belt is cold enough to be a freezer for the early solar system's chemistry, and Ceres is the largest container in that freezer. The slow, cold world also holds a structural secret that took time and close observation to understand. When Dawn first mapped the topography of Ceres in detail, a feature was found near the equator that defied easy classification. It is a tall, bright, conical mountain rising approximately 4 miles above the surrounding terrain, a solitary peak called Ahuna Mons, standing alone on an otherwise unremarkable plain, with no obvious volcanic caldera at its summit, flanked by bright streaks along its flanks that are consistent with the same kind of salt deposits found at Akater. The current best interpretation of Ahuna Mons is that it is a cryovolcanic dome, a place where a mixture of brine and ice and particulate material was pushed upward from beneath the surface under pressure, emerging not in a sudden eruption, but in a slow, cold extrusion, building height gradually the way toothpaste builds a column if the pressure on the tube is steady and slow. On a body without the internal heat to melt silicate rock, this is how geology expresses itself. Not lava, brine, not eruption, a long, cold press. Ahuna Mons is young in geological terms, perhaps only a few 100 million years old, which is young for a feature on a world that has been sitting in the belt for 4.5 billion years. Its flanks are still steep and bright. On a world where viscous relaxation is constantly softening old structures, a feature that is still sharp must be recent. Older cryovolcanic domes may have existed elsewhere on Ceres and have since softened back into the surrounding terrain, leaving only subtle, puzzling low mounds whose origin becomes clear only when Ahuna Mons is available as a comparison. The world that Piazzi found on the first night of 1801, then, is stranger and richer than 2 centuries of treating it as a numbered minor planet would suggest. It has an interior that once held liquid water. It has a crust that flows over geological time like an extremely slow and extremely cold glacier. It has salt deposits forming now at the surface, built from brine that still moves through its fractured rock. It has organics gathered in its northern hemisphere, preserved in a cold that has barely varied since the belt settled into its current configuration billions of years ago. And it has a mountain built by pressure, not by heat, a monument to how geology continues, in diminished and quiet forms, even in places where the obvious energy sources have faded. None of this was known in 1801, when Piazzi wrote carefully in his notebook that something had moved against the stars, and then moved again the next night, and deserved attention. None of it was fully known, even in 2006, when the International Astronomical Union gave Ceres its current designation and placed it in a category it shares with only a small number of other solar system bodies. The designation was correct. Ceres is clearly its own kind of thing, neither a simple asteroid nor a full planet, but the depth of what it is had not yet been measured. The measurements came later, when dawn arrived and lowered itself into orbit and began the slow, methodical work of reading a world. There is something appropriate in the fact that the discovery of Ceres' inner complexity required patience of the same kind that Piazzi exercised on that winter night above the harbor. Not the patience of waiting for something dramatic to happen, but the patience of watching something very carefully over a long period of time, and trusting that the small, consistent changes are telling the truth. The bright deposits at Alcatel do not shout. The water vapor detected by Herschel was barely a whisper above the noise of the instrument. A few photons shifted in their frequency by the presence of water molecules that had just escaped from an icy surface. The organics near Ernutet are not a thick seam of biological material. They are a spectral signature, an absorption feature in a curve on a computer screen, identifying molecules by the wavelengths of light they preferentially absorb when sunlight falls on them. Everything Ceres reveals, it reveals quietly and through instruments tuned to its particular register. This is the quality that Ceres shares, in the end, with the belt that holds it. The belt is not a dramatic place, not in the way that the sun or the gas giants or an active volcanic moon might be called dramatic. It is a quiet place, a preserved place, a region of the solar system where the noise of formation has died away, and what remains is the record, the material memory of conditions that have not existed anywhere in the solar system for more than 4 billion years. Ceres is the largest keeper of that record. Its water and its salts and its organic compounds are not evidence of what Ceres is becoming. They are evidence of what the early solar system was. The frost line that shaped Ceres' formation, that invisible boundary in the ancient disk where temperature dropped low enough for water ice to persist, no longer exists as a boundary. The disk is gone. The conditions that produced it have been absent for longer than the Earth has had a solid surface. But Ceres carries the frost line inside it, encoded in its density and its composition, in the ice that never fully melted, in the salts that migrated upward through its crust from a watery interior that has since refrozen. To orbit Ceres, as Dawn did for almost 4 years, is to orbit a time capsule, not a relic in the sense of something broken or depleted, but a capsule in the strict sense, a container that has kept its contents intact across a span of time that makes all of human history feel like the blink of an eye. The compounds near Ernutet crater have not changed since before the first single-celled organisms appeared in Earth's oceans. The ice in Ceres' mantle predates the Earth itself. The salt at Acater is younger, perhaps still forming, but the water that deposited it has been cycling through Ceres' interior for longer than the moon has been orbiting the Earth. The night Piazzi found his wandering point of light, he did not know any of this. He did not know there was a belt of ancient material where his new object lived. He did not know that the object was large enough to be spherical, or that its interior held water, or that bright deposits of carbonate salt were forming in an impact basin on its surface at that very moment, as he sat in the cold above the harbor and wrote his careful notes. And he knew only that something had moved and that it deserved attention. That attention has continued in various forms across 2.25 centuries, and the more carefully Ceres has been watched, the more it has returned the watching with disclosures of extraordinary gentleness and depth. A little water vapor rising from the surface in the sun's weak warmth, a little salt left behind by brine too slow to see moving, a little organic chemistry settled into the cold of the northern hemisphere and holding its molecular shape against the long passage of time. The cold of Ceres does not feel hostile. From this distance, it feels like a kind of custody. The water it holds has been held for longer than any ocean. The organic compounds it shelters have been unchanged since before anything on Earth learned to breathe. In a region of the solar system built from interruption and incompleteness, where nothing quite became what it was on its way to becoming, Ceres kept something, not alive, not waiting for life, simply present, in the way that the oldest material in the solar system is present, without urgency, without destination, without any need for a witness to continue being what it is. The observatory at Palermo still stands above the city and the harbor. The instruments are different now. The sky above it holds the same stars that Piazzi saw, occupying the same positions relative to one another that they have held for all of recorded human history. And out beyond Mars, along a broad arc between the inner solar system and the gas giants, Ceres turns slowly in the dark, its surface crossing from shadow into pale sunlight and back again every 9 hours, its bright deposit at Akatur catching the weak light and returning it, its deep interior holding the ancient water still, quiet, cold, and composed, the way only very old things can be quiet. The organic compounds near Ernetek crater are small molecules, by the standards of biological chemistry, fragments of the longer chains that living systems eventually learn to build. They have been sitting in the same cold fold of rock and ice since before any living system existed anywhere in this solar system, as far as the record shows. They are not life. They are what preceded it, or what might have, under different conditions, in a different configuration of warmth and time. They are the alphabet, sitting silent on a page, in a language whose grammar was never quite assembled there, but which arrived in similar form elsewhere, carried in the same kinds of rocks, on the same kinds of slow wandering trajectories, to warmer places where the chemistry could continue. Out in the cold, on that small gray sphere above the belt's slow drift, the molecules wait in the only way they can, simply by not becoming something else. The ice holds them, the dark holds the ice, and the dark is very old and very still and in no hurry at all. In the southern hemisphere of Vesta, there is a wound so large it should not exist. 2 craters overlap there, one pressed into the other, each so wide that if either were placed over the continental United States, it would cover most of it, edge to edge, rim to rim. The inner crater, Resilvia, is roughly 300 miles across. Its central peak rises nearly as high as Olympus Mons on Mars, lifted by the rebound of rock that had nowhere else to go after an impact of almost incomprehensible force. And from that wound, across billions of years, pieces of Vesta have been falling to Earth. They fall as meteorites. They fall through the atmosphere in streaks of orange and white, slowing from tens of thousands of miles per hour to the speed of a thrown stone, and they land in deserts and on ice sheets and in fields, and sometimes someone finds them. When they do, they find something particular inside, a mineralogy that does not match the moon, does not match Mars, matches only one known body in the solar system, Vesta. These are the HED meteorites, named for their mineral families, Howardites, Eucrites, Diogenites. They are pieces of a protoplanet's interior, fragments of crust and mantle ejected by the Rhea Silvia impact so long ago that the solar system was still young, still sorting itself, still deciding what it would keep and what it would scatter. Roughly 5 in every 100 meteorites that fall to Earth began their journey there on a world 500 miles wide that orbits between Mars and Jupiter in a silence so old it has no name. Vesta is not a simple rock. That is the detail that settles slowly into full meaning. It is differentiated, a word that means it sorted itself out by density long ago. Heat from the radioactive decay of short-lived isotopes melting its interior, so that iron and nickel sank toward the center, and lighter silicates rose toward the surface. It formed a core, a mantle, a crust. The same rough layering that organizes Earth, that organizes Mars, that organizes most of the rocky planets, formed inside a body small enough that a person standing at its equator would weigh less than half a pound. It became, in miniature, a planet. And then the planet it was becoming was interrupted. The neighborhood it occupied grew too violent, the collisions too hard and too fast to allow continued accumulation, and Vesta arrived at a threshold it could not cross. It remained exactly what it had managed to become, a differentiated protoplanet, a world in arrested development, its interior still layered, its southern hemisphere still bearing the mark of the impact that sent pieces of its crust wandering inward toward the sun. The Dawn spacecraft reached Vesta in July of 2011, slipping into orbit and spending more than a year mapping its surface from various altitudes. From above, those two overlapping southern craters, Venina beneath, Rhea Silvia above, give the asteroid a strange appearance, as though a portion of its lower half has been scooped cleanly away. The exposed strata at the crater walls show layers, basaltic crust, older, deeper rock, material from different epochs of Vesta's formation, laid out in cross-section like pages in a book left open to the right chapter. The light falling on those walls had traveled from the sun across more than 200 million miles of empty space, touched ancient stone that had never been air or ocean or soil, and reflected back toward a camera no larger than a desk. In that returning light was the record of what Vesta had been allowed to become. Far from the belt's main population, gathered in two vast slow clouds that move in formation with Jupiter itself, there is another population entirely. They are called the Trojans. They occupy the gravitationally stable points that exist ahead of and behind Jupiter in its orbit, positions where the combined gravitational pull of Jupiter and the Sun creates a kind of equilibrium, a place where smaller bodies can remain for as long as the solar system itself endures. 60 degrees ahead of Jupiter, along its orbital path, drifts one swarm. 60 degrees behind drifts another. Together they hold an estimated population of over 1 million objects larger than a kilometer across, more bodies than the main belt itself, by some counts, though most are dark and small and have never been visited or named. Viewed from far above the plane of the solar system, those two clouds would appear as diffuse, faintly populated arcs, spread across enormous stretches of Jupiter's orbital path. They do not look like anything a human scale would recognize. They are too spread out to resemble a formation, too thinly scattered to suggest a crowd. They drift They maintain their relative positions, not through any cohesion of their own, but through the quiet geometry of orbital mechanics, balanced between two gravitational influences across distances that would take years to cross at any speed a spacecraft has ever achieved. In that slow drift, they have remained, for most of the solar system's history, unchanged. They are thought to have been captured during a period when the giant planets were migrating, shifting their orbital distances over millions of years, stirring and redirecting the early population of small bodies throughout the outer solar system. Some were drawn inward to become the Trojans. Others were flung outward. The ones that found those equilibrium points stayed and have been drifting there, 60 degrees apart in their two slow herds, ever since. The Trojans are dark. Most of them reflect only a few percent of the light that falls on them, surfaces coated in material so aged and irradiated it has taken on a reddish gray that absorbs rather than returns. Their composition is thought to be primitive, the kind of material that formed in the outer solar system where temperatures were lower and volatile compounds could survive, where water and carbon compounds and complex organics accumulated on and within the rock. They may be among the most chemically primitive bodies in the solar system, preserved in those distant equilibrium points, far from the inner system's heat, for longer than Earth has existed. A mission is currently traveling toward the Trojans to find out. It carries instruments designed to see what those dark surfaces are made of, what they hold, what the outer solar system's original population looked like before the giant planets finished rearranging everything. But that work is still in progress, still unfolding, and the Trojans themselves continue their drift, patient, dark, undisturbed. Some bodies do not stay in the belt or in the Trojan clouds. Some find their way inward, pulled by the slow accumulation of gravitational nudges over millions of years, crossing the distance between the belt and the inner solar system to enter orbits that bring them near the terrestrial planets. These are the near-Earth asteroids. They are not a single population, but a collection of dynamical families, each defined by the shape and extent of its orbit relative to Earth's. The Amers approach Earth's orbit, but do not cross it, swinging inward from the belt and retreating again in long elliptical loops. The Apollos cross Earth's orbit, their paths intersecting the plane of Earth's travel at some point along their elongated trajectories. The Atens orbit mostly inside Earth's orbit, their semi-major axes closer to the Sun than ours, their paths only occasionally extending outward to the belt's vicinity. Tens of thousands of these objects larger than about 500 feet across have been cataloged, and the count is not yet complete. They come from the main belt, mostly, delivered to their present orbits by a combination of forces that work slowly and in sequence. A gravitational resonance perturbs an orbit over millions of years, gradually increasing its eccentricity until the asteroid crosses a threshold and escapes the belt entirely. A slow thermal push, accumulated across an even longer period, moves the orbit slightly in one direction or another until the resonance catches it. The delivery is not sudden, it is a slow migration through orbital space, a gradual accumulation of small shifts until the shift is no longer small, and the body finds itself somewhere entirely new, a planet-crossing orbit, a trajectory that will eventually bring it close to something substantial, that will end in an impact or a gravitational capture, or a slow decay into the Sun. Most near-Earth asteroids do not last long, in astronomical terms. Their orbits are chaotic in the technical sense, sensitive to small perturbations, unpredictable over timescales of millions of years. They will be consumed or scattered before the solar system ends. The belt continues to supply them. The thermal force that nudges asteroids inward toward those resonances or outward away from them is called the Yarkovsky effect, and it is one of the quietest forces in the solar system. It does not act suddenly. It does not release energy in any observable burst. It works like this. Sunlight strikes an asteroid's surface and is absorbed. The surface warms, slowly, the way a stone in sunlight warms. As the asteroid rotates, the warmed surface turns away from the sun into shadow, and in the shadow, it radiates that absorbed heat back out as infrared radiation. The emission is not perfectly symmetric. One hemisphere, depending on the direction and rate of the asteroid's spin, radiates slightly more than the other, and that slight asymmetry, that faint, persistent imbalance in the direction of energy emission, produces a force, a push, measured in millionths of a newton for a body the size of a mountain, almost nothing. Over millions of years, it moves mountains. An asteroid a mile across, subject to the Yarkovsky effect for 1 billion years, can drift tens of millions of miles from where it began. The cumulative displacement is large enough to push a body from a stable orbit into a resonance that will send it toward Earth, or to pull it out of a resonance that would have done the same. It is the reason that calculating the long-term trajectory of any potentially hazardous asteroid is not a simple matter of tracking its orbit and projecting it forward. The Yarkovsky effect introduces a drift that depends on the asteroid's mass, its shape, its rotation rate, its surface composition, its albedo, and the distribution of material within its interior, most of which are not fully known for most objects. To predict where an asteroid will be in a century, researchers must account for a force measured in micronewtons, acting on an object measured in billions of tons. The force is small, the time is long, the accumulated effect is real. There is something in the Yarkovsky effect that rewards a long stillness of thought. It is the kind of force that the daily world contains no preparation for recognizing, not dramatic, not fast, not strong enough to feel, not visible in any single observation. It requires watching the same object across years, measuring its position with great precision, and then noticing that the object is not quite where it should be if only gravity were acting on it. The discrepancy is a signal. The signal is the force. The force is the warmth of the sun, re-radiated from one side of a rotating rock into the cold of space. The imbalance between them nudging that rock, grain by grain of force, year by year, towards something it would otherwise never reach. It is the solar system working on timescales that no individual observation can capture, only the long record of many. The HDD meteorites that began their journey in Rhea Silvia, those pieces of Vesta's crust and mantle, likely owe some part of their eventual arrival on Earth to the Yarkovsky effect. Ejected by the impact, spread across a range of orbits near Vesta, they drifted under the thermal force for millions of years, some inward, some outward, some toward the resonances that would redirect them. The ones that found those resonances were flung into planet-crossing orbits. Some of those fell to Earth. The journey from Vesta to the ground of this planet took, in many cases, tens of millions of years. The meteorites themselves carry that travel time encoded in the cosmic rays that bombarded them in space. The longer they traveled, the deeper the cosmic ray signature reaches into their interiors. Researchers measure it, read it, and arrive at a number, how long this particular stone drifted through space between its origin and its arrival. The answer is almost always a number that lies beyond any ordinary sense of duration, a span in which every civilization that has ever existed would fit without noticing, in which mountains erode and ocean floors remake themselves. The belt is a population, not a collection. The distinction matters. A collection is a set of individual things brought together. A population is a system characterized by distributions, by families, by flows. The main belt contains asteroid families, groups of bodies that share orbits and compositions because they share an origin. They are the fragments of a single larger body that was broken apart by a catastrophic collision at some point in the belt's history. A family is identified by the clustering of orbital parameters, semi-major axis, eccentricity, inclination, values that reflect their common starting conditions and have spread only slightly over the time since the collision. The Eos family, the Themis family, the Coronis family, each bears the name of one of its largest members, and each represents the remnants of an ancient impact. Some of these families are old enough that the Yarkovsky effect has had time to spread their members appreciably, the smaller fragments drifting faster than the larger ones under the same thermal push, the family slowly dispersing across orbital space over hundreds of millions of years. The age of a family can be estimated from how far its members have spread, the Yarkovsky drift rate serving as a kind of clock. Within the belt, some regions are nearly empty. These are the Kirkwood gaps, lanes of sparse population at specific orbital distances where Jupiter's periodic gravitational pull falls into a steady rhythm with an asteroid's orbit, the two periods locking into a ratio, Jupiter completing exactly 2 orbits for every 1 orbit of the asteroid at one gap, or 3 for one at another, or 7 for 3. At these resonance locations, Jupiter's gravity does not tug randomly. It tugs at the same point in the orbit, again and again, each tug adding slightly to the last, the eccentricity of the asteroid's orbit growing over time until the orbit crosses Mars, until it crosses Earth, until the asteroid is no longer in the belt at all. The gaps are maintained by the ongoing removal of any body that drifts into them. They are not places where nothing formed. They are places where nothing can remain. Bodies drift into them, driven by the Yarkovsky effect, mostly, and then they are gone, deflected inward toward the terrestrial planets, or outward toward Jupiter. Their departure quiet, their absence permanent. Those gaps, those dark lanes in the belt structure, are the primary pathways through which the near-Earth asteroid population is replenished. Without them, the belt would lose its inner solar system connection almost entirely. The gaps keep the channel open, a slow, steady drain through which the belt delivers its material to the inner system, one body at a time, over the course of eons. Some of those bodies become meteorites. Some become objects that will eventually be tracked and cataloged and assigned a probability of impact. Some become nothing in particular, their orbits eventually destabilized and their material absorbed by the sun or ejected from the solar system entirely. The belt is not static, it erodes. It has been eroding since the solar system was young, losing mass to impacts, to resonances, to the Yarkovsky effect, to the occasional close passage of a planet. It is less massive now than it was a billion years ago, and less massive then than it was a billion years before that. What remains is a fraction of what once occupied that region, still rich in variety and complexity, still producing meteorites and near-Earth asteroids, but reduced, thinned, a population that has been losing members to the inner solar system for longer than any terrestrial record can reach. Far from all of this, at the inner edge of the belt, Ceres drifts on its own. It is the largest body in the belt, roughly 600 miles across, spherical under its own gravity, internally differentiated in its own quiet way, a world with water ice in its mantle and bright salt deposits in its craters, and a surface that has been slowly creeping over geological time, the icy crust flowing imperceptibly to erase its oldest and deepest scars. It orbits the Sun once every 4.5 years in a near circular path that keeps it between roughly 2, 5, and 2, 99 astronomical units from the Sun. Its surface temperature rarely rises above about minus 100 degrees Fahrenheit, even at the warmest point of its day. It turns once every 9 hours, its day short, and its year immense, its interior maintaining a quiet thermal regime shaped by ancient radiogenic heating, now largely spent. The probe does not belong entirely to the same story as Vesta or the ordinary chondrites scattered through the belt. It is its own kind of world, not a fragment of something larger, not a differentiated protoplanet whose crust has been stripped by impacts, but a body that retained its volatile compounds, that held its water through the early violent period of the solar system's history, that built inside itself a chemical environment distinct from anything else in the inner solar system. The bright patches at Octo Crater, visible even from Earth as variations in the reflected light from Sirius disk, are sodium carbonate, salts left behind as briny water migrated up through fractures in the ice-rich crust and evaporated into the vacuum at the surface. The process that deposited them may still be continuing, slowly, on timescales of thousands of years. Ceres exhales, not dramatically, not in visible plumes, but in the slow release of water vapor detected by instruments designed to see what the eye cannot, a quiet exhalation into the surrounding space, a remnant of the interior activity that once generated more heat than it does today. Near Ernetet Crater, the Dawn spacecraft detected organic compounds during its time in orbit. These are carbon-bearing molecules of the kind that, on Earth, are associated with the chemistry of living things, not life itself, but the molecular vocabulary from which life is built. They were found on the surface of a world that formed more than 4 billion years ago in the outer part of the asteroid belt, preserved in cold and darkness and vacuum, undisturbed across a duration so long that it contains the entire history of life on Earth, several times over. Their presence does not imply that Ceres hosted life, but it says something about the distribution of organic chemistry through the early solar system, that these compounds formed readily, that they formed in multiple environments, that they survived in the cold of the belt, while the inner solar system was still warm and chaotic and rebuilding itself from one impact after another. The asteroid belt, viewed from a great enough distance, would appear as a faint haze, barely distinguishable from the background, a region of diffuse reflected light surrounding the Sun, between the orbits of Mars and Jupiter, too thinly populated to see any individual member. The whole population, adding up to less than 4% of the Moon's mass, spread across an enormous annular volume of space. The haze would be slightly brighter in some places, dimmer in the lanes of the Kirkwood gaps, with Ceres and Vesta faintly distinguishable by their size and brightness from the hundreds of thousands of smaller bodies around them. It would not look like a collection of worlds. It would look like nothing in particular, only at close range, only in the data returned by spacecraft that have spent years traveling to reach individual members of that haze, does the belt resolve into what it actually is, a museum in the loosest possible sense of interrupted formation. Each body is a record. Ceres holds its water and its salts and its organics. Vesta holds its differentiated interior and the memory of the impact that scattered pieces of it across the inner solar system. The ordinary chondrites hold the first moments of the disk, chondrules, calcium-aluminum inclusions, the dust that first aggregated under van der Waals forces in the early disk's midplane. The carbonaceous chondrites hold water and amino acids and nucleobases. The iron meteorites hold the cores of differentiated bodies that were broken apart so long ago that their fragments have been wandering the solar system for longer than complex life has existed on Earth. All of it drifts, slowly, under the influence of gravity and the Yarkovsky effect and the gentle pressure of resonances building over millions of years. The belt delivers its contents to the inner solar system. Meteorites fall. Near-Earth asteroids accumulate in their planet-crossing orbits. Dust filters inward on a slow spiral, contributing to the zodiacal light, that faint diffuse cone of illumination visible just before dawn or just after sunset, in the direction of the sun, the belt's finest material, catching the sun's light and returning it to Earth's sky. The zodiacal light is the belt's most constant presence in our experience of it. Not a meteorite, not a tracked object, just a glow, a diffuse reminder that the region between Mars and Jupiter is not empty, has never been empty, and will continue sending its material slowly inward long after any individual body within it has been consumed or scattered. Vesta's southern craters, stacked one inside the other, stand as the largest preserved record of what the belt's early collisional history looked like. The forces that shaped those craters are the same forces that prevented the belt from building a planet. Collisions too fast and too frequent for accumulation, gravitational perturbations that sent bodies into intersecting orbits, the belt's own history working against itself. Resilvia is not just a scar, it is a record of the collision regime that defined the belt, translated into a topographic feature large enough to be visible across hundreds of millions of miles of space with the right instruments. The central peak, rising in the middle of that enormous basin, is rock that once lay deep beneath Vesta's surface, lifted by the rebound of the impact event into a prominence that has stood undisturbed since the solar system was perhaps a quarter of its current age. The pieces of that rebound, scattered outward, drifted for millions of years under the Yarkovsky effect and the nudge of resonances, and some of them arrived here. They sit now in museum collections and research laboratories, small, dark, or pale or glassy stones that look like ordinary rocks until someone cuts them open and sees the mineral assemblage inside, the pyroxene and plagioclase of eucrites, the orthopyroxenite of diogenites, the mixed regolith of howardites, and recognizes the signature of a differentiated world. They are pieces of Vesta's interior, carried here by the same slow processes that govern the belt's entire dynamical life, and they carry within them the same ancient story that every asteroid carries, in its own way, the story of material that gathered, that differentiated or did not, that was struck and scattered or survived intact, that drifted inward under forces too small to see and too persistent to resist. That persistence is the belt's most essential quality, not its violence. The impacts are ancient, most of them, and the current belt is far less active than it was in its first billion years. Not its emptiness. It contains hundreds of thousands of cataloged bodies and millions more uncatalogued. Its persistence. The same bodies that formed in the early disk have been drifting in similar orbits for most of the solar system's history. Their orbits slightly modified, their surfaces slowly altered by space weathering and micrometeorite bombardment, but their bulk composition largely unchanged since the first few million years of their existence. They are the most stable records of the solar system's formation available to any instrument. The planets remade themselves through accretion and differentiation and volcanism and erosion. The belt preserved, in the quiet of a near-Earth asteroid's orbit, a slow ellipse that brings it from beyond the orbit of Mars down to within a few million miles of Earth before swinging it back out again. The Yarkovsky effect is still working. One hemisphere of the asteroid warms in sunlight. It turns away into shadow. It radiates. The force is a few millionths of a newton against a body that might weigh several billion tons. The drift is a few feet per year, perhaps. Less for a larger body, more for a smaller one. Over a century, the asteroid moves a few miles from where a model that ignored the thermal force would predict it to be. Over 10,000 years, it has moved far enough to change the calculation of whether it will strike Earth, or pass harmlessly by, or miss entirely. The numbers matter in that specific and practical way. But beyond their practical weight, there is something else in them. The image of a stone in sunlight, warm on one side, cool on the other, drifting through space under the force of its own warmth. Patient, slow, indifferent to the scale of time over which it works. The Trojans drift ahead and behind Jupiter, dark and cold and slow. The main belt drifts between Mars and Jupiter, its population slowly thinning, its inner edge delivering a steady supply of material through the resonance gaps to the inner system. Ceres holds its water and its salts in the dark beneath its cratered surface, its interior cooling over geological time, but still holding what it has always held. Vesta's wound faces away from the sun for half of every 4-year orbit. The southern craters in shadow, the central peak of Resilvia, dark and cold and still, and somewhere, in a desert or on an ice sheet or in a field, a stone from this ancient population waits. It has already arrived. It fell years or decades or centuries ago, and it lies now in darkness below the surface, or it has been found and sits in a tray in a laboratory. Within it are chondrules formed before Earth existed, calcium aluminum inclusions that are the oldest solids in the solar system, minerals that last saw liquid water on an asteroid more than 4 billion years ago. It arrived here the same way everything in the belt moves, slowly, under forces too small to feel, over timescales too long to hold in the mind all at once, and it holds within it, in its mineral structure, in its isotopic ratios, in its tiny preserved spheres of ancient silicate, the quiet record of a disk that formed and gathered and paused and has been drifting in that pause ever since. The warmth on one side, the cold on the other, the gentle, irresistible drift. A meteorite sits on a laboratory bench in a room where the air is still. It is the size of a closed fist. It is dark gray, almost black, with a thin glassy crust where its outer surface melted and re-solidified during the seconds it spent falling through the atmosphere, a crust so thin that the gentlest scratch removes it, revealing the ancient material beneath. The room around it is ordinary, fluorescent light, a tile floor, the quiet hum of ventilation. And inside this common, unremarkable stone, sealed since before the earth existed, there are small round beads of glass, each one no larger than a grain of sand, each one a perfect sphere, each one older than anything else in this building, or this city, or this world. They are called chondrules. They formed in the protoplanetary disk, that vast rotating sheet of gas and dust that surrounded the young sun, when brief intense bursts of heat, reaching temperatures of nearly 2,000 degrees Celsius, melted droplets of silicate mineral in free-floating space. The droplets cooled within hours. They cooled before they could settle, before they could join anything, before the disk had decided what it was becoming. And so they froze mid-fall, mid-process, mid-decision, and became the small glass spheres now resting inside this dark stone on this ordinary bench. To hold a meteorite that contains chondrules is to hold a sealed record of a heating event that happened 4.5 billion years ago and lasted perhaps no longer than a single night. The sphere is geometrically perfect in a way that nature rarely produces. Not the rough tumble of a river stone or the pressed flatness of sediment. A true sphere formed in microgravity, where no surface pulled the cooling liquid into any preferred shape, where surface tension alone drew it inward and held it round until it hardened. Under a microscope, Woodwald, the quiet hum of ventilation, recording in their geometry the brief thermal history of a droplet that fell through space without touching anything else for millions of years before finally settling into the rock that eventually fell to Earth. No one knows with certainty what caused the heating. Several good explanations exist: shock waves moving through the disk, electrical discharges, the bow shocks of planetesimals moving at speed through the surrounding gas, and each carries real evidence, and none is yet ruled out. And the honest answer is that the exact mechanism that formed the most common objects in the most common class of meteorite is still, after more than a century of study, not settled. The chondrules themselves do not say. They record the temperature. They record the cooling rate. They do not record the cause. That part of the story is written in material that has long since been scattered. What they do record is a moment, a specific physical, irreversible moment in the early disk, when matter that was dust became briefly liquid and then became glass. In the billions of years since, those beads have been pressed into rock by the slow accumulation of other dust and grit around them, carried through the solar system inside the bodies that eventually became asteroids, shaken by impacts, warmed by radioactive decay, eventually broken free by some collision in the belt, sent inward through the solar system along a long elliptical path, and finally heated one last time in the thin upper layers of Earth's atmosphere. And here they are now, in this quiet room, still round, still intact, still carrying within their glassy interiors the frozen record of a few hours' worth of heat in a disk that no longer exists. Inside the same stone, embedded in the dark matrix around the chondrules, are objects older still. They are too small to see without instruments. They are a few thousandths of a millimeter across, small enough that hundreds of thousands of them could fit inside a single chondrule, and to find them, researchers must dissolve the surrounding rock in strong acid, a painstaking process that destroys most of the meteorite to free the few grains it contains. What remains after the acid has done its work are tiny crystals of silicon carbide, or graphite, or sometimes diamond, minerals with isotopic compositions so unlike anything else in the solar system that they could not have formed here. The ratios of their isotopes match the nuclear processes that occur inside specific types of dying stars: red giants, asymptotic giant branch stars, supernovae. Each grain is a remnant of a star that no longer exists. Each one drifted through interstellar space for millions, possibly hundreds of millions of years before the cloud that would become our solar system began to collapse. They are called pre-solar grains, and they are the oldest material ever measured, not old in the way the chondrules are old, which is to say, old within this solar system, but old in a deeper sense, old before this solar system was a solar system, old when this part of the galaxy was just a slow, cold cloud of gas and dust between the stars. To find a presolar grain inside a meteorite is to hold, in a laboratory on Earth, a physical object that was made in the body of another star and that has survived the death of that star, Millions of years of interstellar travel, incorporation into the collapsing nebula, the heat and pressure of the early solar system, billions of years inside an asteroid, and a final plunge through the atmosphere. The grain did not know any of this was happening. It simply existed, its crystal lattice unchanged, its isotopic signature intact, waiting for nothing, meaning nothing, carrying within its structure only the physical record of the nuclear reactions that made it, in a place and time so remote they can be reconstructed only through the logic of atomic physics. The meteorite that contains them, dark, rough edged, still resting on that bench in that still room, has been on Earth for a matter of months or years. For everything before that, it was elsewhere. For most of its existence, it was the interior of an asteroid moving slowly through the belt in the cold dark between Mars and Jupiter, unchanged, undisturbed, waiting for a collision that would eventually send a fragment inward toward the sun. The stones that fall through Earth's atmosphere come from many places in the belt, and they are not all the same. The most common are the stony meteorites, and within that class the most primitive are the carbonaceous chondrites, dark, fragile stones rich in carbon and clay minerals, and sometimes carrying the faint chemical traces of water that once flowed through their parent bodies as liquid long ago. The clay minerals they contain, hydrated silicates, minerals in which water molecules are bound into the crystalline structure, could only have formed in the presence of liquid water. The parent asteroid must have contained enough radioactive material in its early history to warm its interior above the freezing point, allowing liquid water to circulate through its pores and cracks, altering the original dry minerals into the clay-like forms now seen in the meteorite. That liquid water has been absent from the asteroid for more than 4 billion years. But its former presence is written into the stone, in the structure of every clay grain, in the way the minerals have been subtly chemically changed. The water that circulated through those asteroids has a measurable character. Water molecules contain hydrogen, and hydrogen exists in two forms: ordinary hydrogen, with a single proton in its nucleus, and a heavier form called deuterium, with a proton and a neutron. The ratio of these two forms in a sample of water varies depending on where and how the water formed. In the outer solar system, where temperatures were very low, chemical processes concentrated deuterium into water molecules more efficiently, producing water with a higher deuterium content than water formed closer to the sun. The water now locked into the clay minerals of carbonaceous chondrites has a deuterium content that closely matches the deuterium content of Earth's oceans, much more closely than the water found in most comets. The implication drawn carefully from the comparison of these ratios across many different samples is that a significant portion of Earth's water was delivered by asteroids, bodies from the outer part of the belt, water-rich, arriving early in the planet's history and contributing to the oceans that now cover most of its surface. The water in those oceans, and the water that has moved through living things for billions of years, or the water in the clouds now moving slowly across whatever sky lies outside this room, some fraction of it came from beyond the frost line, locked in minerals, delivered by slow and ancient collisions, and then released. The asteroids did not intend this. They had no role in mind. Their water was simply there, carried in the chemistry of their formation, and when they fell, it was released into a new system, where it eventually found its way into oceans and rivers and the cells of living things, where it still circulates tonight. Among the clay minerals and the water-altered silicates in carbonaceous chondrites, chemists have found other things. In a meteorite that fell in Australia in 1969, landing near the town of Murchison, Researchers working to understand the chemistry of primitive meteorites found amino acids, the molecular building blocks from which proteins are assembled in living cells. Not one or two, but dozens of different amino acids, including several that occur in living organisms and many that do not. The amino acids in the Murchison stone were not contaminants from Earth. Their isotopic composition differed measurably from terrestrial amino acids, reflecting the different isotopic environment of the outer solar system. They formed in space, on or inside the parent asteroid, through chemical reactions driven by the warmth of radioactive decay and the presence of liquid water. They were there in the rock before the rock arrived, waiting in a form that required no biology, no cell, no enzyme, only the right molecules and enough warmth and time. Alongside the amino acids, the meteorite carried nucleobases, the molecular components of RNA and DNA, the molecules that carry and copy genetic information in every living organism now alive, not assembled into any functional sequence, not arranged into any strand, just the bases themselves, present, stable, waiting in the mineral matrix of a 4 billion-year-old stone. Sugar molecules of the kind used in RNA were found in a different carbonaceous chondrite, identified in recent years, adding another piece to the slow inventory of biology's raw materials distributed through the solar system. None of this means life came from asteroids. That question is open, and the honest answer is that no one yet knows where life began or exactly how. But what these molecules demonstrate is that the chemistry of life did not require Earth to invent it from nothing. The molecular vocabulary of biology was already present in the material from which the planets formed, scattered through the asteroids, locked in primitive meteorites, available in space before any ocean existed on any world. Life, when it arrived, was working with material that had already been prepared across billions of years and hundreds of millions of kilometers in the interior of bodies too small to ever become planets, drifting slowly through the cold. There is a particular kind of stillness in thinking about this, not the stillness of an empty room or a quiet landscape, something older, the stillness of chemical processes running at geological pace, of molecules forming and holding their form for billions of years without change, of material that has circulated through stars and clouds and accretion disks and planetesimals, and finally into living cells, each step in the chain following from the one before it, with no intention and no direction, simply the logic of chemistry and physics playing out at whatever scale and pace the conditions allowed. The amino acids in the Murchison meteorite did not move toward Earth. They did not go anywhere. The Earth moved around them, and the meteorite moved with it, and when they met, the chemistry that had been waiting for 4 billion years was simply added to a new system that was already its own 4 billion years old. The meteorite itself is now stored in a controlled environment. Its remaining mass is measured precisely. Portions of it have been distributed to researchers in many countries who have each extracted different information from their small share. Some of it has been dissolved. Some has been thinly sliced and mounted on glass slides and photographed under polarized light, where the mineral grains catch the light differently depending on their crystalline orientation, appearing in colors, deep blue, pale gold, faint pink, that correspond to no visible feature of the rock in ordinary light, only to the invisible geometry of its internal structure. Some of it sits in sealed containers in the dark, unchanged since it arrived. The parts that have been studied carry the most detailed record of any sample of the early solar system available on Earth, a record of isotopic ratios and mineral assemblages and organic chemistry that has been read and reread and argued over and refined across more than 5 decades of research, and that is still not fully understood, and that still regularly produces new findings when new instruments are brought to it, because the information stored in that dark, fragile stone is more densely layered than any instrument has yet been sensitive enough to fully read. A single gram of Murchison meteorite contains thousands of distinct organic compounds, each with its own structure and its own story of formation. The tools required to identify and count them all did not exist when the meteorite arrived. Some of them were not discovered until decades later, when instruments capable of detecting molecules at lower concentrations were developed and turned, for the first time, on samples that had been waiting patiently in their sealed containers. The meteorite did not change in that time. The science changed around it. Other meteorites carry other records. The iron meteorites, dense, bright when cut and polished, showing the interlocking crystalline patterns of nickel-iron alloy that formed over millions of years of slow cooling deep inside a differentiated asteroid, carry within their structure a clock. The Widmanstätten pattern, those long diagonal bands of different iron-nickel phases visible on the cut surface, could only form if the metal cooled at a rate of roughly 1 to 10 degrees Celsius per million years. Too fast and the crystals would be too small to see. Too slow and the pattern would be different. The pattern that formed tells researchers precisely how slowly the interior of a long-dead planet-sized asteroid cooled inside its insulated mantle, and from that cooling rate, they can estimate the size of the parent body, the depth at which that particular piece of metal solidified, and the time scale of the whole process. The rock carries within its visible surface structure the complete thermal history of a world that no longer exists. These parent bodies, the differentiated asteroids that once had iron cores and rocky mantles that were large enough to melt internally from the heat of radioactive decay, were mostly shattered long ago by collisions in the early belt. What remains of them arrives as meteorites, the iron from their cores, the stony iron mixes from their core mantle boundaries, the basaltic rocks from their surfaces, each type of meteorite sampling a different layer of a world that no longer exists as a world. When those pieces are sorted and matched by their isotopic chemistry, identifying which fragments came from the same parent body, a partial picture of a whole collection of lost worlds begins to form, worlds that formed in the first few million years of the solar system, worlds that differentiated, developed geology, and then collided and fragmented before Earth had finished forming. Their remains now sit in museum collections and laboratory drawers, labeled and cataloged, the broken pieces of dozens of worlds that had a beginning and a middle and then an ending without ever producing anything that breathed or turned toward the light. In the belt itself, the fragments continue drifting. Between the remaining large bodies, the dwarf planet, whose bright salt deposits catch the distant sunlight, the scarred protoplanet still mantled in basalt from its own ancient eruptions, and the hundreds of thousands of smaller bodies from gravel piles to mountain-sized rocks, the space is mostly empty. The belt is not the crowded obstacle field of older imagination. Most of any given volume of the belt is nothing. Vacuum, cold, silent, sunlight diminished to roughly a quarter of its strength at Earth's orbit, the stars visible without atmosphere to scatter or absorb them, the distant sun small and bright, and without warmth enough to feel. Between the bodies, the interval is enormous. A spacecraft crossing the belt from one side to the other passes through that empty space for years and may come close to nothing at all. The emptiness is itself a record. The material that was once in that space, The Earth masses of rocky and icy material that was present in the belt's formation region before Jupiter's gravity stirred and scattered and eventually expelled most of it is gone. Some of it now makes up the inner planets. Some of it was flung into the outer solar system. Some of it was scattered entirely out of the solar system's gravitational hold, and now drifts in the space between stars, unattached to any sun, cold beyond cold, carrying in its minerals the chemical signatures of a solar system it has long since left behind. The empty space in the belt is not absence, it is the shape left by a process that happened once and cannot be undone. The bodies that remain are the ones that found stable enough orbits to survive across geological time. They are old, not because they were protected, but because they were lucky. Lucky in the specific sense that their orbital paths did not bring them close enough to the resonant frequencies of Jupiter's gravity, often enough to be decisively redirected. The ones that wandered into those resonances are gone, their orbits stretched and deformed over millions of years until they crossed the path of a planet and were either captured, collided, or thrown outward. The ones that remain are the survivors, and their survival carries no particular quality or fitness, only the randomness of where they happened to be when the solar system was still sorting itself out. And yet they carry so much. Inside the body of a C-type asteroid, dark, rich in carbon, orbiting quietly in the middle reaches of the belt, the material is essentially unchanged from the early disk. The heat that would have altered it never came. The water that would have stripped away its organics was too little and too brief. The collisions that would have shattered its internal structure left only mild fracturing, enough to loosen the bonds between its surface grains, but not enough to melt or recrystallize the chemistry within. Inside, at depth, below the loose, dusty surface layer that absorbs and re-emits sunlight every day of every year across billions of years, the mineral chemistry is close to what it was when the disk was young. Not identical, radioactive decay has warmed it. Water has passed through portions of it. Some minerals have been gently altered, but closer to the original than anything else available to study, closer to the beginning than any rock on Earth, where plate tectonics and erosion and volcanism have remade the surface so completely that no surface rock older than about 4 billion years has survived, and the first half-billion years of Earth's history are geologically invisible. The asteroids preserved what Earth destroyed, not because they tried to preserve it, not because the material was special in any way that called out for protection, because they were small and cold and in a region of the solar system that settled into a stable enough pattern to leave them mostly undisturbed. The same gravity that prevented a planet from forming in the belt also prevented the processes that would have erased the chemical record stored in its rocks. The frustration that left the belt as rubble rather than a world also left it as an archive. The same force that scattered most of its material also preserved the rest, in conditions that kept it close to original. This is the particular quality of the belt, not what it failed to become, but what it managed, through the specific circumstances of its failure, to remain. A grain of dust drifted through the protoplanetary disk 4.5 billion years ago. It was a fraction of the width of a human hair. It drifted in the disk midplane, moving slowly, colliding gently with other grains, adhering to them through the weak attractive forces between surfaces at close range. Over thousands of years, it became part of a pebble. The pebble became part of a boulder. The boulder became part of a body, several kilometers across, tumbling slowly through the young belt in a region of the disk that was still rich with other bodies, still colliding and clumping, still moving toward the threshold of planetary assembly. And then Jupiter grew large enough, and the orbital resonances began to push and pull at the belt, and the body that contained that grain of dust was struck hard enough to fragment into smaller pieces, and those pieces were struck again and again until the particular piece of rock that contained that grain settled into an orbit that happened by chance to be stable enough to survive for billions of years. Inside that rock, through all of it, the grain of dust was unchanged. It did not know it had been inside a protoplanet, and then a boulder, and then a fragment, and then a meteoroid, and then finally a stone falling through a blue sky toward a pale surface. It was simply a grain, a cluster of silicate molecules, a few mineral crystals, the whole of it a few millionths of a meter across, and it persisted because persistence requires nothing but the absence of the conditions that would cause change, and in the cold dark of the belt, those conditions were mostly absent. The sky above the laboratory where that grain now rests inside its meteorite is dark tonight. The belt is above the horizon. From this latitude, in the direction of the constellation that marks the ecliptic plane, the plane of the solar system, the flattened sheet of material that was once the protoplanetary disk. The belt itself is invisible from the ground with the naked eye. Its individual members are too small and too dark and too far away. Only the brightest, seen under very dark skies with binoculars, show themselves as slow-moving points of light against the fixed stars. The rest of them, hundreds of thousands of bodies ranging from gravel to city-sized mountains of ancient rock, move in silence through the space between Mars and Jupiter, each one carrying its own internal record of the first few million years of the solar system. The light from the sun that reaches them tonight is old, not old in the way the rocks are old, only 8 minutes old, the travel time from sun to earth, a few minutes more to reach the belt, but old in the sense that the sun itself is old, and has been burning for 4.5 billion years, and the photons reaching those dark surfaces tonight were generated a moment ago by the same fusion processes that have always powered it, in a star that has barely changed in the time it has taken the solar system to cycle through its current configuration. The asteroids absorb some of that light and reflect some of it. The absorbed portion warms them slightly on their sunlit sides, and as they rotate, that warmth is re-emitted as infrared radiation, a faint, slow release of heat from rock that has spent billions of years in cold space. The emission is not even one hemisphere facing the sun and then slowly turning away as the asteroid rotates is always slightly warmer than the other. The warmth it releases as it turns into shadow pushes back against the asteroid in the direction of emission, a force so small it cannot be felt, measured only in micronewtons, acting on a body that weighs perhaps billions of tons. But over millions of years, that force accumulates. It does not stop at night, because there is no night in the belt, in the way there is night on Earth, only the slow rotation from sunlit to shadowed and back endlessly, and each rotation adding its almost nothing of force to the long total. Slowly, across those millions of years, the asteroid drifts, its orbit shifts, its semi-major axis changes by tens of millions of kilometers over geological time, carrying it toward or away from the resonance zones that govern whether it stays in the belt or eventually leaves it. This is how the belt moves its pieces. Slowly, without urgency, in increments too small to see in any single year or century, but real and cumulative across the timescales the solar system works in, which are not human timescales and do not hurry for human comprehension. The meteorite on the bench was once an asteroid drifting in the belt. Something shifted its orbit, the accumulated warmth of billions of sunrises, or a glancing collision, or the slow pull of a resonance zone it drifted into over millions of years, and it began to move inward. Its orbit crossed Mars. It came closer to the Sun. Eventually, it crossed the path of Earth, and on one particular night in one particular year, it entered the upper atmosphere at roughly 20 kilometers per second, and the air compressed in front of it and became bright, and for a few seconds something fell through the sky that had not been on Earth before and would not be there again, and then it was on the ground, and it cooled, and eventually someone found it and brought it inside, and it has been resting there since, in a room with fluorescent light and a tile floor and the faint hum of ventilation. Everything it contains has been there since before the Earth. The presolar grains inside it, those fragments of dead stars, each one a few thousandths of a millimeter across, each one carrying an isotopic signature foreign to this solar system, have crossed the most distance. They formed inside the atmospheres of red giants and the expanding shells of supernovae, in processes of nucleosynthesis that our sun's own core cannot produce. They drifted through the interstellar medium, through that slow cold dark between the stars, for perhaps hundreds of millions of years. They were incorporated into the cloud that collapsed to form the sun and its disk. They survived the heat and pressure of the early disk without melting, though the warmest regions would have destroyed them, and settled into the outer, cooler regions where the carbonaceous asteroids formed. They have been inside those asteroids ever since, and now they are here. There is no word for the kind of old they are. The number 5 billion, 6 billion, more is accurate but not felt. What can be felt, approaching it slowly, is the number of transitions, star to dust, dust to cloud, cloud to disk, disk to planetesimal, planetesimal to asteroid, asteroid to fragment, fragment to meteorite, meteorite to grain on a laboratory slide. Each transition took geological time. Each left the grain itself unchanged. It simply moved from one context to the next, carried by forces it did not experience and could not feel, through environments that would destroy most things, persisting because its crystal structure was stable enough, and its circumstances lucky enough, and the universe old enough to give it time to arrive. The laboratory is quiet. The stone rests.